This video will demonstrate how to write oxidation-reduction reactions. And oxidation-reduction reactions are otherwise known as redox reactions, so I'll be using that nomenclature throughout the rest of the video. So when you're in a laboratory environment, writing redox reactions is actually a little bit easier because you have some visual indication of what your reactants and your products are. So in this case, you see that a small piece of aluminum foil is added to a solution of hydrochloric acid. And when that is done, the aluminum foil dissolves, a gas is produced, and the solution turns cloudy, and then it clears. So for this solution that we have, it's fairly obvious that the aluminum is one of the reactants. And then you also have HCl as a reactant, but HCl, of course, because it's a strong acid, will be fully dissociated into its H plus cations and its Cl minus anions. So number one, the aluminum foil dissolves, so we know that one of our reactants is aluminum. This is a reactant. Now we have two other possibilities for reactants, H plus or Cl minus, or both. But what we see is that a gas is produced. And you really have two choices for gases. You could have hydrogen gas, or you could have chlorine gas. And since it's fairly unlikely that in a laboratory environment you'd be producing chlorine gas, since that's fairly dangerous, H2 gas is your most likely product. So our product is hydrogen gas. And that means that our other reactant is this H plus. The Cl minus, that's just a spectator ion, so it's not participating in the reaction, it's just there. And then our final clue that we have, it says the solution turns cloudy and then it clears, so there are no other solid products being produced. So we can be fairly certain that we've identified our reactants as solid aluminum and H plus, and our product as hydrogen. So once you've determined what your reactants and your products are, then what you want to do is you want to go look at a table of standard reduction half reactions. And just as a warning, these tables are very large. The table that we've placed in your iBook and that I've copied here is an abbreviated table that we're using as an example. And it's much easier to work from from a small table like this. When you go to work from the larger table like you will in lab, it will be more confusing because you'll have several pages of reactions to choose from. But for example purposes, what we want to do is we want to find some reactions that use our reactants, which are solid aluminum, H plus in the aqueous phase. So these are reactants. And we want to find reactions that produce our products, which in this case are just hydrogen gas. So with the reactants and products identified, you go to the table of standard reduction reactions to find reactions involving your reactants and products. And in this table, we see that the only reaction involving aluminum is reaction 9, but there are actually two choices for reactions involving H plus, reactions 2 and reaction 6. But reaction 2 doesn't generate hydrogen gas, so that reaction is not a possibility. So that indicates that our two half reactions that we're going to be interested in are reaction 6 and reaction 9. And what's important to realize is that all redox reactions are actually the sum of two half reactions. So these are going to be our half reactions. Now these tables of reduction half reactions, in these tables, all reactions are written in the reduction direction. So they were all being written in the direction where electrons are being consumed. But in actuality, in redox reactions, one reaction produces electrons, and that's an oxidation reaction, while the other one consumes electrons, and that's your reduction reaction. So what you have to figure out is which reaction is proceeding in the reduction direction and which is proceeding in the oxidation direction. And in the case of an experiment that you can view, it's usually fairly easy to determine which reaction is going which way. So reaction 6 is proceeding in the direction given because we know that hydrogen gas is being generated and we know that H plus was our reactant. For the other reaction involving aluminum, however, this reaction actually has to be written going the other way when we go to do our overall redox reaction, because we know that we started with aluminum, solid aluminum, and we ended up generating Al3 plus, which we couldn't see because it's a dissolved product. So reaction 6, this is going to be our reduction reaction, and reaction 9, which we're going to rewrite going in the other direction, this is going to be our oxidation reaction. So down below, I've already written the reactions in their proper direction. Here's our reduction reaction. Here's our oxidation reaction. And to get the overall reaction, all we're going to do is add the reduction half reaction to the oxidation half reaction. But since the oxidation half reaction generates the electrons that are consumed in the reduction half reaction, the number of electrons being generated has to equal the number of electrons being consumed. So before we can add them together, all we have to do is multiply our reactions by a factor to get the number of electrons equal. So we're going to multiply the bottom reaction by 2, and we'll multiply the top reaction by 3. So let's look at the top reaction first. 3 times 2 is 6. 3 times 2 is 6. And 3 times 1 is 3. And on the bottom reaction, 2 times 1 is 2. 2 times 1 is 2. And 3 times 2 is 6. So now we have 6 electrons being generated and 6 electrons being consumed. So we can go ahead and add our two reactions together. And we get, on the left-hand side, we get 6H plus 2 solid aluminums going to produce 3 hydrogen gas plus 2 Al3 plus cations. And I just realized there's a mistake right here. This should say aqueous. But that is it. So that is our overall redox reaction. You can see that we didn't have to write the electrons on either side because both of the electrons canceled out. So that's how you write a redox reaction.